Alright, so today we're going to talk about one of the most important rules with derivatives, and that is our chain rule, as you can see here on the screen. So, kind of like the last video, I'm going to just gloss through the PowerPoint a little bit faster, just because I want to do my own thing here, because some of these examples may be a little bit too much in terms of going a little more in depth than I think we need to here. So, I'm going to jump back and forth in this. Um, First example here, you see this, they call it a combination of a quadratic function and a cubic function. And the idea of this function is, as you see here, it's something being cubed. That's the key part. That's the main thing. But the difference is, instead of it being something like this, and we know how to find this derivative of x cubed, we get a 3x squared. Well, the difference is, in this case, we have something inside the base. It's not just a plain base of x. So it's going to build on the same principles, except there's an extra step we have to do because of the fact that this is not an x. When this base is something different than an x, we have an extra step. Now the good news on this one, and I'll tell you about the chain rule, you'll see formulas, you'll see other steps here. I'm going to jump right into it and tell you what you need to do here. So again, you know how to find that derivative right there. We've been doing that from the beginning, or for a while now. Now in this problem here on the right, what happens is anytime that you see the base is basically not equal to x, then it's going to trigger this chain rule. And I'll show you how it works. It's really not a lot to it. So the first step of finding the derivative, number one, nothing changes. We have this to the third power. Okay, so the rule is the same. We bring the 3 out front and we put the 2 down, just like you saw over here. Okay, the core function, that's all the same. The difference now is because, like I just pointed out in red here, because this chain rule, because you have a base, it's not just a plain x. And I'm talking about the inside of that parenthesis. What we have to do is we have to multiply by the derivative of that base. In this case, the derivative of the inside, whatever that base is, whatever's in that parenthesis, if that's not an x, you have to multiply by the derivative of that. So we multiply by the derivative of x squared plus 4, we get a 2x, and that's our derivative here. That's the extra step we have to do. So I can move that all in front, and we have kind of a simplified, cleaned up form right here. So like I said, just like normal, this is just like this one over here. We bring the old power out front, multiply it, and then we drop the power down by 1. And notice in this example here on the left, the base is x. When I take the derivative, the base is x. That doesn't change. The base never changes. Well, here, my base is x squared plus 4. When I do the power rule, the base stays as x squared plus 4. When I take the derivative of it, that's this chain rule part that I multiply on. And the chain rule, you're going to see a theme here. You're always multiplying your answer by the chain rule, by the derivative of the inside. Okay? So, kind of talk about what's going on here in this particular problem. They break it down by the functions. And I'm not, like I said, I'm not a huge fan of this because it seems sometimes to make things more complicated. So I like to just show you exactly what the answer is. So I'm going to go through these a little bit faster and give an example how it's going to work when we find these derivatives. Okay, so they talk about composite functions, and you've had this before at some point where one function's inside of the other, and that works perfectly fine. But like I said, I think it's better, easier to understand, and quicker if we go this route that I'm showing you here. So, talking about the general power rule on the top here, that's what I just mentioned a second ago, where if you have x to some power n, the derivative is n times that same x, and you drop the power down by 1. Okay, so that is always going to be the case here. So the difference, and you see, this is the formula, this is the notation, when I have anything to the n power. Okay, if it's just a plain x, or if it's some complicated parenthesis, the rule is just like I demonstrated. You put the n out front, you keep the inside the same, and you drop the power by 1. The new part is this on the right. This is the chain rule, which says you take the derivative of the inside here and you multiply to the answer that you just attained. Okay, so this is just some formulas to show it. It's the same thing. We're going to be doing this all day here. So a similar kind of problem here. We have something 3x plus 1 to the fourth. Now, like I said, it does not hurt when you're doing these if you want, and you say, well, let me think of it as, what if I had something like this? What if I had y to the fourth? How do I find the derivative of that? You know, if I had some function equal to this, the derivative would be 4y to the third, okay, following your power rule, your normal general power rule that we did. Well, over here, it's the same thing. When I find this derivative, I take this power of 4 right here. That comes out front. The base does not change one bit, and then you reduce the power by 1. Okay, so again, that's the same power rule we've been doing, but now is where the chain rule comes into place. And the chain rule says you take this, and I should put chain up here, but it's the derivative of that inside, and it's basically just a 3 that you multiply by. That's your chain rule. Okay, derivative of whatever that inside was. So when I clean this thing up a little bit, I'll put the 3 out front, 3 times the 4, and I end up with this right here. And that is your derivative in a simplified form. Not sure if you can see that. That's supposed to be my derivative sign. Let's do that again. There's a derivative right there. Okay, so that's all there is to it. Like I said, you don't have to worry about composing the functions or changing the form and all that. You know, now you may get a homework problem where we have to do that, and I'll show you how we do those. It's really a minor step, but that's the process. You take the derivative as you normally would and just ask yourself, is the base something other than an x? Well, in our case, the base it's 3x plus 1, so I'm going to take the derivative of that, and that's what I multiplied on the end to get this answer. Okay, so you see here, I'll kind of look at how they work this out. They've done that, exactly what I did earlier. Remember, bring the 4 out front and drop the power down by 1. And then this is the step that I don't always write. I go right to the answer of 3, but you're multiplying by the derivative of that base, and that's where this 3 comes from. So I kind of go right to this step here. Okay, and then of course, they end up with the same thing that I had here. Once I combined and condensed everything, bring the 3 up to the front and multiply it by the 4, and you have your derivative. Okay, so same kind of process here. You're going to bring the 7 out front, and you're going to drop the power down by 1. And remember, I can't say this enough, don't change that base. That 7 right there, that power is on the x cubed plus 4, and that stays there. Now it becomes a 6, and then we're going to multiply by the derivative of this parenthesis. So that is going to be a 3x squared, and I just condense that and move that in front. We get a 21x squared, parenthesis x cubed plus 4 to the power of 6. Okay, so like always, pause this if you need to look at it, and unpause when you're ready to roll. We'll go forward here. Now this one, same kind of process here. Okay, now before I do this one, I want you to you got to start looking at things as a big picture and saying, okay, this is kind of like when I have 1 over x cubed. Yeah, it's a lot more complicated, but that parenthesis cube on the bottom is this. So what I want you to think of it is, that's like having an x, there's my negative, to the negative 3, and we know how to find that derivative. Okay, when I say go get the derivative, we get the negative 3 out front, and remember the rule, I'll write it out here. We subtract 1 from the power, and that's why you get a negative 4. So that would be the derivative of this. This thing right here, the derivative is that down there. Okay, so kind of use that as a basis. Well, we know how to do that. Well, it's the same thing over here. What I'll do is I'll bring this whole thing up top and have it as a negative 3. Now notice I still have that d dt in front because that's my command, that's my instruction to find the derivative. So I have not done the derivative yet. I've just rewritten the original. Okay? And then, I actually write this, I forgot. We're on a slideshow here. So That's what they did right here. Exact same thing that I'm erasing right here. They brought it up to make it a -3. And then the next step, you take the derivative. So we bring the -3 out front, we drop the power by 1, and then remember, this part is the chain rule. This is the new thing of today. If that inside, if that parenthesis, anything other than x, or in this case a t, then you have to multiply by the derivative of that whole parenthesis. Well, the derivative of the whole parenthesis comes up to be a 2t plus 1, and then we can clean up our answer. Now I want to make sure everyone sees how we went from here over to here. Okay, so the -3 stays on top. The parenthesis 2t plus 1, that stays on top. And that whole thing, that's the 3 terms to the -4, that goes back down to the bottom because that's what a -4 power is. That's where the +4 power appears. Okay, so again, I'm just using the idea of ask yourself, what's the big picture? Yeah, there's some complicated parenthesis there, but the big picture is it's just something on the bottom to the 3rd power. That means that something is to the -3 power. And that's what we're going to use to find the derivative. And the chain rule is just one new extra step that you're adding on literally to the back end of your problems. Okay, you're just multiplying by the chain rule. Okay, so these are, again, rewrites stating the same thing. And again, I don't want to get you too bogged down in this. I want to show you more of how to actually find it here. So we'll get to another example here. We want to find the derivative of m prime of x of the composite function m of x. Well, same thing as before. Look at the big picture. Now, they're going to call this a u, and I'll show you how they write this. Okay? They want you to look at it as the big picture is you have something that's going to the 3/2 power. Okay? Now, if it was just this, I'll write down, this is easy. We know how to find that derivative. Okay, but of course it's not that. It's this thing in there. This is the item that's inside. That's the piece that's in there. Okay, so what they're going to do is they're going to just figure out, I know how to find e prime of u. It's all of this right here. And we know how to find this. That's the chain rule. So how they're going to approach this one, and I'm not saying it's wrong, it's just a different approach, but it's the same kind of thing here, is to find the derivative. Start right here, okay? So I'm going to jump all the way down to here. Same old rule. Take the power, bring it up in front. Then you leave the base the same. And I'll even note that right there. And then the rule of the power rule is you drop the power by 1. You subtract 1 from the power. So the power used to be 3/2, now it's 1/2. And then this part right here is the chain rule, where we take the derivative of that base, that parenthesis, and that's how we get the 6x. The derivative of 3x squared plus 1 is a 6x, so the chain rule says multiply by that. And then they simplified a little, simplified it on the right there. That 6x comes up front and it becomes, multiply that by 3/2, that's where you get the 9x from, and the other part stays parenthesis 3x squared plus 1, all to the 1/2 power. Okay, now I'll point out something, I don't even want to write this, but this is the most common mistake people get when they do the chain rule. They get the idea of multiplying by the derivative, but what I see all the time is people make this the 6x. So they do the power rule correctly, where they bring the 3/2 up front and they drop it down to 1/2. But instead of keeping the base the same, they put the 6x, the derivative, inside, and that's the part you cannot do. That's why I wrote earlier, this has to be the same base, and the chain, the derivative, comes on the back side. It always multiplies to the back end. Never affect the base when you're doing the basic power rule. Okay, so that's the hint that I'm going to give you, and I'm going to keep repeating that because that happens all the time. Okay, now the chain rule works in every other situation. For example, if you saw this function, let me give you another one here. Let's say we had p of u equals e to the u. Okay, now you guys remember that the derivative of e to the something is just e to the something. Nothing changes. Okay, this applies only when the power is a nice single x or u in this case. So when you see something like this problem over here, and I want to find this derivative, Now I'll kind of show you what they do. Same kind of concept, okay? So jump right down here to the bottom. This is the part that I want to show you. Okay? When you have e to something, anything, the derivative is always e to that same thing. It's just a carbon copy. That's what you get, okay? The derivative, right there, I'm doing the derivative, of e to anything is just e to that something. Now, if that was just something was an x or a u or a y or whatever, then you're done. But this part right here is a chain rule that says, well, that power is a little more complicated than just a plain x. It's a 2x cubed plus 5. So I have to apply the chain rule, which says multiply it by the derivative of said power. And the derivative of 2x cubed plus 5 is a 6x squared. So that's what multiplies to the back end of your derivative. So you still do the derivative like you normally would do. You just have to multiply by the chain rule on the back end. And then, of course, to clean it up, you don't have to move it up front, but generally you put the x's and then the coefficient of 6 and the x's that are normal powers, you put them up front, and you usually put the e to the back side. Okay, but it's still three things multiplied together, so technically the order doesn't matter. But that's usually what you're going to see when you check your answer, say in the back of the book or in practice exercises, or even when you look at the answer in the homework. Okay, so here's another one, same kind of thing. If I had this, you remember this from the other day, the derivative of natural log of x. Okay, derivative of the natural log of x is simply 1 over x. Remember, it's just 1 over whatever's on the inside. Well, on this one, it's the same thing. When I find that derivative, it's 1 over all of that mess right there. Okay, that entire inside of the natural log, the derivative is 1 over that. But, as you can bet, if it's just a plain x, we're done. But if it's something other, since this is not equal to x, then we have to do the chain rule, which is derivative of that inside. So I take the derivative of x squared minus 4x, and I get a 2x minus 4, and that's the chain rule. That's what multiplies there. So the core idea is still the same. We have a natural log of something. Natural log of anything, the derivative is 1 over that something, that item. That's this part. That's the normal part. The other part is going to be the chain rule. So then, of course, the last step is we just have to go in, put the 2x minus 4 on the top of that fraction. So it'll be 2x minus 4 all over the x squared minus 4x plus 2. And that's how we arrive at our answer here. Okay? So you kind of see that they're, oops, sorry, go back. You see here they're doing the same problem. They're getting the same answer that I had here, and I'm just going to erase what I wrote. And same thing, if you look at the very bottom. Like I said, that middle step isn't absolutely necessary. Now, if you're going along and that does make sense to you and that works for you, then I'm going to say keep doing it. Keep working as long as you understand it. But I like to just jump right to this bottom step right there. Okay, remember this is what I wrote. 1 over the inside. This is the chain right here. And then this is the simplified answer right there. Okay, so again, pause, check that out, make sure you're okay with it, and then when you're ready, unpause and just continue on. Okay, so this last slide kind of tells the story that I like on everything. It's the 3 derivatives we've had so far. Anything to any power, the answer is, well, right here you apply the power rule and you multiply by the derivative of the inside. Okay, if you have natural log of anything, you take 1 over that anything and you multiply by the derivative of that anything, of that piece right there on the inside. Same thing when you have e to something, it's just a carbon copy, e of that same thing, but your chain rule is in all 3 cases, you multiply by the derivative of whatever that was. In this case, multiply the derivative of that power. Okay, so a couple more examples here. We have derivative of e to the 2x. Well, I already know right now the answer is e to the 2x, because that's what the derivative of e is. But because that power is something other than an x, I have to multiply by the derivative. So the derivative of the power 2x is just a 2. e to the 2x times 2, so our derivative is actually 2e to the 2x. So it's still a copy, but there's going to be a little extra added on there. Over here, same thing. I'm taking the natural log, the derivative of a natural log. That gives me 1 over that item. And the chain rule over here is we multiply by the derivative of that inside that parenthesis. So the derivative of x squared plus 9 is going to be a 2x right here. And then that, of course, because you're multiplying to a fraction, that's always going to put it on the top, the numerator, 2x over x squared plus 9. Okay, then our last case, we get a little complicated part. Now, this is where it starts getting interesting because you're going to have a chain rule of a chain rule, and you'll see how this breaks down here. Okay, first step, you have to start looking at what's the big picture, kind of like outside working in. This, even though it's a very complicated inside, it is just something to the third power. So I take the 3, I drop the power down by 1, and remember what I wrote earlier, you keep that base the same. Then the chain rule says we need to take the derivative of this inside, which is the 1 plus e to the x squared. So now I've got this first half done. I now need to find the derivative of this for the chain rule. In doing that, I have to think about, well, what's this derivative? Well, the derivative of 1 is just nothing. The derivative of e to something is e to the x squared over x squared. Then, because again, that's not just a plain x squared, I have to multiply again by the chain rule, the derivative of that power. That's going to come out to be another 2x. So I get a chain rule on top of a chain rule, and this is going to happen a lot. The more complicated functions you get a chain, another chain, just depending on how far you need to go. Now we just move everything out front, parentheses in the back, and we get a 6x e to the x squared, parentheses 1 plus e to the x squared to the second power. And that's it for that one. Okay, so again, pause, check that out, and I'm going to get this ready and do a little of our homework assignment here. So once again, we're in the 176 course, looking at our assignments here. Maybe, there it is. We're on homework number 8 now for week number 8, almost halfway through. And we have a handful of problems, but some of these you'll see, they do go very quickly. Excuse me. So some of them will go fast. Some of them are going to be a little more work. And then some of them are just asking you to sort of break the problem down and not actually looking for the answer. So let me zoom this in a little bit here. Okay, replace the question mark with an expression that will make this valid. Okay, so remember the rule. We take the derivative of e to this complicated power. Well, e to anything is the same thing, but the rule is we have to multiply by the derivative of the inside, so the power. The derivative of that power, x squared plus 9, is going to be x fourth plus 9 is going to be 4x to the third. And that's the extra piece. That's the chain rule right there that I was talking about. Okay, so again, as we keep going through these, some of these I'm going to have more writing. Some of them I'm not going to have much. That's just all there is. But if you need to pause, feel free to pause. Now we get to our typical problems here. I want to find this derivative. So here's the function. And I keep saying look at the big picture. What I'm getting you to see is we have something to the 6th power. And I don't care what the base is right now. I just see something to the 6th power. So my first thought is take that something and apply the power rule. So notice I didn't deal with the inside, but that's the power rule. Remind you again, the base doesn't change at all. If that base was parentheses 2x fifth plus 7, when you apply the power rule, it's still parentheses 2x fifth plus 7. Where the derivative comes in is in the chain rule, where we get that 10x fourth right here. That's the chain part. The derivative is always multiplied to the back end. So now I'm just going to clean this up a little bit, and I make this a 60x to the 4th times all of this. And that's as far as you can simplify. That's it right there. So that's what I'm going to type in here. 60x to the 4th. And we have parentheses 2x to the 5th. Plus 7, and that is all to the 5th power, and see what we get, and we have our good job. Okay, so just want to make sure again that you're understanding where I'm getting each of these from. Okay, so as I go on to number 11, I think is next. Trying to erase this, sorry. Okay, number 11. We have a natural log. We have a 2 out in front. We have a big complicated piece inside the natural log. So like I said, don't be afraid to rewrite this as an easier problem just to remind you of what the steps are. Because we've done this derivative before when the inside was just a plain x. The problem is now we're getting advanced. Sometimes we forget that basic step. So like I said, if I had this problem and I want to find the derivative, we know it's 1 over x. Okay? Now, if there was a number in front, just want to remind you how that works. When I find that derivative, all I do is I multiply that number times 1 over x. Apologies, not natural log of x. 1 over x. So it's 2 times 1 over x, or simply 2 over x. So those are just reminder problems. Okay, now we look at our big picture right here. We have that 2 out in front, and the main thing I want you to see is you have a natural log. And I don't want you to get hassled with the inside. Just think, okay, that's a natural log. I know the derivative of every natural log. It's 1 over all of that, exactly as it is. Okay? Now, because that's something more than an x, the rule is we need to multiply by the chain rule, which is the derivative of that inside parenthesis. So the derivative of 8 is nothing. The derivative of 3x squared is a 6x. And now I just clean up a little bit. Everything that's on the top is the 2 and the 6x, so that's my 12x. And on the bottom is that right there. And that's, if I can factor simplify, I would do that. But in this case, I think I have everything as far as I can go. 8 plus 3x square. And there is our answer. Okay, so let's look at number 15. Eventually 15 will show up here. Okay. All right, 3 parts. So they want you to find the derivative and find the equation of the tangent line of f at the indicated value of x. Find the value of x where the tangent line is horizontal. So there's 3 things they want us to do here. We're going to go one at a time. Number 1, let's just find the derivative. Okay, so one step at a time. Don't think too far ahead here. Okay, so that's the problem. That's the function. The derivative, remember, is 1 over that entire inside. Again, that's because that's the rule for dealing with any natural log. Then I'm going to multiply by the chain rule, which says the derivative of that inside. Well, the derivative of 6 is nothing. That becomes a negative 18x, and the other part is going to be a 32x cubed. And then, so my derivative is simply, let's combine all this. It's going to be negative 18x plus 32x cubed over all this. Okay, so that should be my answer for part A. What's good about this is if we happen to get it wrong, we won't mess up the other 2. We'll have a chance to correct this before we try to do the other parts, because if this is wrong, we're definitely going to get the second and third parts wrong. So this is sort of the nice part of this style is we get to check our answer before we go too deep into this. So I think I did everything right. Yep, so that's confirmed. Now remember, they want the equation of the line tangent to the graph of f at x equals 1. Okay, so think of the process on this one. We have some function that, don't worry if you don't even know how this looks. That's why we have a procedure. We're going to figure it out. This is the derivative. Okay, so this is my derivative right here. That is the formula for the slope of every single tangent line. Well, How do we know which one it is? They tell us it's at x equals 1. So to get the slope, I'm going to plug in a 1 for every single x. Okay, so I'll move that over here. F prime of 1 equals negative 18 plus 32 all over 6 minus 9 plus 8. And like always, some of you are going to say, well, I could have done all this one step earlier. You don't have to write every step out here. I'm just doing this to make sure we all see what we're getting here. But it looks like I'm getting a 14 over 5. Now that's my slope. So remember, slope of the tangent line is what the derivative is. We have this slope right here. Okay? And we've done this problem before. We just didn't do it with this type of equation. Our next step is I need to go figure out, okay, what's a point? They want an equation of a line. See that right there? So in order to get the equation of a line, we need the slope, which is m equals 14/5. And also, we need a coordinate. We need some other point. Okay, so now I'm going to get rid of some of this here to show you the next step is, I know that it's a tangent line, so it's got to touch my graph at that one point. Well, they told us where that point is. That's when x equals 1. So to get the actual coordinate, because I need an xy, I know it's going to be 1. I need to plug 1 into the original problem. So again, reminder, when you plug in the number to the derivative, it's telling you the slope of the tangent line. When you plug the number in, like right now, to the original function, it's telling you the y value. So that's what I'm getting right here. So we get natural log of 5, I think. Okay? So I'm going to leave it as natural log of 5 for a second. Now, just to get your calculator out, you can kind of see here, natural log of 5 is this 1.609437, etc. Okay, now I don't want to write that whole long decimal, so that's why I'm just going to leave it there temporarily and see how this works. So we need to find the equation of the tangent line. Okay, so we know the slope, 14/5. We know the coordinate, 1 comma natural log of 5. Now I'm going to plug all that into my good old point slope formula. Like I said, you did this last week. You just did it with a much more tamed problem. But this is no different than what we've been doing, where we plug in and we go get the coordinate. We get the slope. We use the derivative to get it. Like I said, the difference is this is not a normal equation, and it's definitely not a normal, derivative here. So we get y minus natural log of 5 equals 14/5 parenthesis x minus 1. Okay, now this is my equation. All I have to do is just move this over a little bit. And we should have our answer right there. Okay, and that's what I'm going to plug in to this. So y equals 14/5 parenthesis x minus 1 plus natural log of 5. Okay? And we get a nice well done here. So let me clear this off and see if you can make sure you're clear on that one. Now the last part, I'm going to erase the screen because we've got a lot of mess here, but we've got the first two right. And then select the correct choice. Now remember, what they're asking for is find the values of x where the tangent line is horizontal. So we talked about this a little bit. A horizontal tangent line is going from right to left, perfectly straight, as in right, left, level is what I mean to say. So that has a slope of 0. So what they're saying is, find me a tangent line that has a slope of 0. So you see this right here? That is my formula for every single slope of every tangent line. I'm going to let that equal to 0. So this is my formula right there. So remember, when you plug in a number, like we plugged in number 1, it gave us the slope. You plug in the number 2, it's going to give you the slope. Well, we want to go backwards. I want to know what x's will give me a 0. So what I do is I say, let's let the derivative equal to 0. Again, something we've done. And then the new thing is, remember, when a fraction is equal to 0, it doesn't matter what the denominator is. All you have to do is let the numerator be equal to 0. And you have to solve it there. Now the rule is we're supposed to factor this out. So I'm going to factor out a 2. We get an n and x. Apologies. Factor the right side when it's equal to 0. First step, pull out the greatest common factor. So let me pull out a negative 2x. It's going to leave me with a 9 minus 16x squared. And then I keep factoring. And this is the difference of 2 squares. 3 plus 4x, 3 minus 4x. So my solutions are right here. Set that equal to 0, we get x equals 0. Set the next parenthesis equal to 0, we get x equals negative 3/4. And set this one equal to 0, we get x equals positive 3/4. So the question they ask you is the value of x where the tangent line is horizontal. Now, I'm going to plug this in, and I'm going to have a little guess here. Now, I'm supposed to check something, so before I check the answer, we have to make sure a couple of things. Number one, when I plug in a number, these are all x values, okay? At the bottom here, x equals 0, x equals negative 3/4, x equals positive 3/4. We have to make sure when you plug something in, it never violates the original domain. Okay, now we didn't talk about the domain, but the rule always is your domain for a log, this inside has to be greater than 0. You can't have 0, you can't have any negatives. So I don't need to necessarily find the domain, but what I should do is before I hit check answer or submit my answer, I want to make sure these 3 values exist in the domain. Easy way, just go plug them all in here and just make sure it doesn't give you a negative in here. So when I plug in a 0 for x, I get a 6. I don't care what the natural log of 6 is, I just know that that's going to be good. It's positive, so that's going to work. If I plug in 3, let's go with 3/4 here, you just want to make sure you don't get something that turns it negative, and by eyeballing it, I think I'm going to be fine here. Doesn't look like I'm going to get a problem, but if any of these caused a problem where it made it a negative, inside the natural log or any log, you have to throw it out. But I think all those work. Yep, they do. And that's it for that question. Okay, so a number of steps. It's a repeat of what we've been doing. The difference, like I said, though, is that we get a much more complicated function to start and we get a more complicated derivative. Okay, now, same kind of thing here. Remember the rule. When we are looking for our derivatives, we have to play, in this case, this is a division, we have to use our quotient rule. So remember how this works. And I'm going to go step by step here. Okay? So the derivative. It's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That was our quotient rule that we talked about last video here, okay? So I'm just going to plug things in here. The bottom is x cubed, okay? The bottom squared is x7 squared, like that. The derivative of the top is 1 over 4 plus x. And remember, with our new chain rule, we're supposed to multiply by the derivative of the inside. Well, that's actually a 1. We're okay. Didn't really mess anything up. Then we subtract the top times the derivative of the bottom, which is 7x to the 6th. Okay? So now, we have a multiple choice problem here, and I want to make sure, like always, we look at all 4 choices. Now, sometimes they're going to leave it as it was. Sometimes they're going to want you to do a little bit more work. And that looks like that's the case here right now, what they're doing. They're trying to make this problem a little bit more clean. All right, so if you look at all those answers, none of them seem to look exactly like mine. We'll talk about that here. So I'm going to clean it up a little bit. This is an x seventh over 4 plus x. This is a minus 7x sixth natural log of 4 plus x. All of that is over x to the 14th. Okay. So now I want to clean it up a little bit more. And what's going to happen is, to get this, this is known as a complex fraction, where you have a fraction within a fraction, like in the numerator here. So what I'm going to do is I'm going to multiply this by 4 plus x to get rid of that. But in order to do that, I have to multiply everybody by 4 plus x, including this one down here by a 4 plus x. All of that just to make that cancel. So now what we end up with is an x seventh minus a 7x sixth 4 plus x natural log of 4 plus x. Oops. Notice too, when I multiplied this 4 plus x, when it multiplies here, it does not multiply and mess with the log. That log is always 4 plus x. It's like multiplying by a 3 or an x. It gets really shipped to the front. That's why I put it with the 7x to the 6th. Same thing with the bottom. I have an x to the 14th, and I have a 4 plus x. Okay? Now you notice none of these answers look, just looking at my denominator, I have an x to the 14th, 4 plus x. Well, they all have a 4 plus x down here, but none of them have the right power, and there's a couple other issues here. So what happens is, look at my numerator. I can factor out an x to the 6th. What that gives me is an x and a minus parenthesis 4 plus 7. Forgot my 7. Only pulled out an x to the 6th from both pieces here. So that's a 7. That's a parenthesis, supposed to be a parenthesis. 4 plus x, natural log of 4 plus x. And the reason I do that is, on the bottom we have x to the 14th. So this x6 will cancel with these, and it leaves me with 8 of them. So now I can kind of see my answers. I have an x8th, 4 plus x on the bottom, just like that, just like that. Now I just want to see which numerator matches. So look at that bracket. We have an x minus 7, 4 plus x, natural log of 4 plus x. That's my answer right there. So, like I've said many times before, the question is, make sure you get your algebra here. Lots of algebra. That's all this is. If you go back and look at this entire thing, the only calculus is, once we have this formula, is I did a derivative right here. I did a derivative right here. That's it for the calc. Everything else that's ugly in this problem is just algebra, algebra, algebra to get it to look like this answer right here that we wanted to get. Okay, so lots of extra steps. I'll let you pause it there and look at it if you need to. All right, let's look at number 23. Okay, so 2 parts. Find the derivative and then find the equation of the tangent line, just like we did a couple problems ago here. So step 1. Now you see, as these problems get more and more complicated, you're going to need more space. Like, for example, I can tell you right now, my space is not going to be enough, but I'm going to work on this regardless. Okay, now the big picture is, you need to get a derivative. Well, I have this and I have this. I have 2 things I'm multiplying together. This is going to be the product rule. Another rule we learned recently. And this is the part where it does start to get, I'll say, a little out of control for some people, is You're learning a rule, then you're learning another rule. Now you're going to start combining rules. You're going to do multiple things at the same time. But you just have to stop and think carefully what's going on. Okay, so watch what happens here in every step that I do. So remember the product rule. We have two pieces. I'll call this first and second. And the second, yes, is that big parenthesis with the power 3. So the rule is we take the first times the derivative of the second. Well, the derivative of that is 3, 4 minus x squared, the power rule that we've been doing. But now we have our new chain rule, which says I got to multiply by the derivative of the inside, and that derivative of 4 minus x is a negative 1. Okay, first times derivative of the second. Then you take second as it is. When I say first and second, it's exactly as you see them. Second times the derivative of the first. And I didn't need this line here. It's not a quotient rule. So I'll kind of narrate that out. First derivative of the second. Then second and derivative of the first. That's how we got these pieces right here. And like always, we need to clean this up a little bit if we can. There's not a whole lot to clean up on this one. We have a negative 3x parentheses 4 minus x squared, and then we have a plus 4 minus x cubed. Okay, now I'll do this next step. You don't have to do this, but it's a good habit to get into. If I look at this whole thing, I see that both terms have a 4 minus x. So I can factor out the smallest power of them. That leaves me with a negative 3x and a single 4 minus x to the first. So you see how I factored that out. I took a 4 minus x out of both pieces. I took 2 of them out of here, and I took 2 of them out of here, and that's why we left out when I factored those. Like I said, this is good algebra practice because this is what you're going to have to do time and time again. So if I just keep cleaning this up a little bit, that bracket becomes negative 4x plus 4. I can even go a step further, and I can pull out a negative 4. And that leaves me with just an x minus 1. That's my derivative right there. Okay, and notice that's not even the end of the problem. That's just one part. So if I plug that in here now, that's the cleaned up answer here at the bottom, but I should theoretically be able to plug any of these in. Okay, any of these pieces I can plug in there, and it's going to give me the right answer. So let me just say, I'm fairly confident mine will work on the bottom, but let me just pick this middle one. In fact, let me just pick this one right here without any simplifying, any cleaning up, or not much at least. And it should work when I try to plug in the derivative, but we'll find out. So let's say, I'll go to this one with the orange cross off. Negative 3x, parentheses 4 minus x to the second, plus parentheses 4 minus x to the third. And there's my answer. If I plug that in, it would work. If I plug this last one in, they're all the same derivative. They're all going to work. Okay, now remember what we're supposed to do. We need to go and, why I told you this is all optional, this cleaning up, because you're still going to get the answer no matter what you use. Every one of these are derivatives. So our rule is we want to know what happens at x equals 2. So I need two things. First, I need to get the slope. So to get that, I'm going to find f prime of 2. Then I need to get the point, and to do that, I'm going to get f of 2. Same thing we've been doing here. So f prime of 2, doesn't matter which one I do, but I'll just go to this one right over here. F prime of 2 is going to give me negative 4 times 4 minus 2, which is 2 squared, and for 2 minus 1, which is 1. So it looks like I get a negative 16. Now, if I was to plug it into the one we did right here as well, we should get the exact same thing. If I found f prime of 1, we get a negative 3 times 3 squared plus 3 cubed. It's close. Okay, so what I'm realizing what it is. I'm supposed to find f of 2. 1 was from that other problem we had earlier. F prime of 2, if I plug it into the answer that we submitted, which we know was a correct one, and I'll tell you, if you know that one's correct, that's actually the one you should be using. That's why I'm doing it now. So when I plug in 2, I get negative 6. I get a 2 squared plus a 2 cubed. So that gives me a negative 24 plus 8. And yep, we get a negative 16. Same answer we had over here. So this is the slope. Now we have to find the points. Remember, you go back to the original equation and plug in the 2. We get 2 times 2 cubed. That's from this, the original function right here. Plug in a 2 for that. You get a 2 times 4 minus 2, which is 2 cubed. And that gives us a 16. So that means we have a coordinate of 2 comma 16. Okay, so I'm going to erase the derivative since we know we got that right. Erase the function because that's good. What we have to plug in now is that, remember, they're looking for the equation of the tangent line. Every time you use the derivative to find the slope, and then you use that original equation to get an actual point, and that's what you're going to plug into our slope-intercept formula. Okay, so I think I got enough space here. Y minus y1 equals m times x minus x1. That's what we're plugging into, all the stuff that I have on the right side of the screen. So I'm going to replace the m with the negative 16. I'm going to replace x with the 2 and y with a 16, or the x1, y1. We're going to plug in the point, plug in the slope, see what we get. So we get a y minus 16 equals negative 16 times x minus 2. And now they want you to answer in the form of y equals. So we should have a negative 16x plus 32 plus the 16. I can simplify this one, so I'm going ahead and doing it. And I think we get a negative 16x, make sure that's all right, plus 48. That's what I'm plugging right into here. And there's our answer on number 23. Okay. Same kind of stuff here, and this chapter you're going to find it's exactly the same work as you just got finished doing. The problem is it's going to be a little bit more intensive because of what you have. Okay, here we have 3 parts. Give the domain of f, the domain of g, and then the domain of m, where m is the composition function here. So one at a time. Starting with right here, the f function, we have natural log of 5u. Okay. So remember the rule. The inside has to be greater than 0. So I take that inside as it is, and I just say it's got to be greater than 0. Divide both sides by 5. That's my domain right there. Okay, everything greater than 0. Now remember, they want interval notation. So that means we use that parenthesis or bracket. Well, we're not, normally it would be from minimum to max. Okay, that's your interval notation. All right. In this case, it's going all the way from 0, and we don't include 0, all the way up to infinity. And infinity always has a parenthesis. So there's our domain of the first one. For G, it's a similar rule. For square roots, the rule is this has to be greater than or equal to 0. So the difference is on a natural log or any log, you cannot have a 0 in there. You can only have positives. In a square root, again, you can't have negatives, but you can have a 0. So it's a slight difference. I set that whole inside greater than or equal to 0, and I get x greater than or equal to 0. So my domain here is almost the same, except for we have the bracket instead of a parenthesis for the 0. Always a parenthesis on the infinities, though. So that's the only difference of those two. Now the difference of f of g of x, m. Okay, so if you haven't seen these composition functions in a while, where you put one function into another, I'll give you a quick rundown of this. So they said m of x equals f of g of x. Okay, so what that means is you take the f function and you put the g of x inside of it. All right, so my f function, remember, is natural log of 5u. We're going to replace that u with whatever g of x is, so it is 5 times the square root of 3x. Okay, so that's what's going on here. And again, they ask the question, well, what's the domain? Well, there's two things. Number one, we can't pick, we definitely, this root right here, it still holds out. We cannot do any negative numbers. But now we have to make sure that this whole inside is greater than 0. And you're going to find when you divide by 5, you square both sides, whatever the case, you're still getting all this. But I cannot have an actual 0. That's really what the case comes down to is. This is our minimum, but let's try 0. When you plug in 0, oh, it gives us a 0, so we can't use that. And usually what it's going to turn out to be, it's going to be the lesser of the two. So it's, this one is everything above, this one right here is everything above 0. This one is everything including 0. Our answer is usually the one that's the more restrictive. And that's what we get here on this one. So play with it. If you're not sure, does 0 work? Go plug it into here. If does -1 work? Go plug it in and you'll know because you get an error. It just does not work out in your calculator. Okay, so let's look at number 31. Okay, find the derivative and simplify. This is a complicated looking derivative, but it's not as bad if you just remember the rules. Now, the first part is, it may not be clear how they wrote it, and I'll say that it's not always the most obvious, but here's what it is. It's 2, and this is the entire power of 2. So think of it like that. It's 2 to that power. Okay? So if you remember, the derivative is, normally it's 2 to whatever. So let's go over here. If I ask you to find the derivative of 2 to the x, you guys remember the rule is, well, it's 2 to the x times that natural log of 2. Remember that? So here it's the same thing. It's all of the same thing. Copy exactly as it is, no difference, times the natural log of 2, but then remember the chain rule. That's the part that we have to add. In this case, it's multiplying, but that's the additional piece that goes there. You have to take the derivative of all of this inside right here. All of this is going to be the chain rule. Spelled chain rule wrong, sorry. So the derivative of that whole inside turns out to be 4x third minus 2x plus 3. Okay? So now we try to see which one most looks like the answer we have. Now, number one, if you have a base 2, like we have here, your answer has a base 2. This then has an e and this one has an e. These are out. It's got to be one of those first two. So both of them have the correct first part where we copied it. Both of them have the chain rule. One of them has natural log of all this, but we talked about it. It's just natural log of that. Process of elimination, we only have one choice, and it's going to be A. Okay. So that's it for that one. Not as bad. They don't have you to simplify or go any further. It's just getting you to understand that you're using a couple of rules together. Okay, so let's look at number 35. Okay, we're still in section 3.4. Research group using hospital records. All right, so we have a formula, and they ask us to find the rate of change of pressure. So I've said this many times, and I'll say it again. If you have a function, this one that equals to pressure, and they want you to find the rate of change or instantaneous rate of change, that always means go find the derivative. Well, the derivative of 60 is nothing, so that's gone. The derivative of the natural log is 1 over that inside, just like that. And then remember, times the chain rule. Well, the derivative of x plus 3 is just a 1. So my derivative is a nice simple function. It's just 35 over x plus 3. All right, so the rate of change at the end of 10 years, so remember, we plug in the 10 right here. We get 35 over 13, and that is your pressure. They want us to type an integer or a decimal rounded to the nearest hundred. Well, let's get the calculator out here. 35 divided by 13 equals, and that's what we have. So to the nearest hundredth, yeah, we should have 2.69. And we'll check that one and see what we get. And that looks good. Okay, now part 2, the rate of change at the end of 30 years. So it's the same thing now. We're going to take our derivative, and we have to find kind of a new problem. We need to find p prime of 30. Okay, now notice again, it's change of pressure. That tells you derivative. So p of 30 is 35 over 33. And once again, we need to get that decimal. And it's 1.06 to the nearest hundredth. And just because the first one said nearest hundredth, make sure you read yours. Yeah, we're also nearest hundredth. Once in a while, they change it up on us. All right, and the last one. Now we want to find p prime of 60. So we get our 35 over 63, and that's all there is to this. The 3 parts are really not that bad. All right, bunch of 5s. Remember though, to the nearest hundredth is 0.56. And that's it for this one. Okay. And I think, no, maybe 39 is also a part. Nope, now we move into section 3.5. So at this point, you should be able to do at least 1 through 35 of your homework. Oh, I lost it here. Okay, no worries. You should be able to do the first 35 questions of your homework. Next video I'll have is 3.5, and it's only going to be a few homework problems. It's going to be a little bit more to it, but should be about the same amount of work here. So again, like always, reminder for your Monday quiz. Make sure you get that in, and I'll send you another video shortly. Have a good one.